Hello TADHack, my name's Sam Machin. I'm going to be showing you what I've been doing this weekend. I think we'll jump straight into the demo and I'll come back and tell you how it works.
Right, so what we have is two of these little dev boards I've been working on. This is a Raspberry Pi Pico, so the microcontroller version of the Raspberry Pi, and then this is a breakout board. So what we have is a microphone unit, an I2S microphone, a little speaker, audio amp driver, I2S decoder, so an output, and a small speaker connected. And then just some buttons and LEDs really, and some debugging and test points. Now, so we have two identical boards. These are both connected to the Wi-Fi, the green light on, so we know they're already connected to Wi-Fi and connected into MQTT. And these are simple walkie-talkies basically, so I can use the press to talk button on this one and talk in here, and you hear the audio coming out of the other one. So you can see also when I press the button on this one, the red light will come on saying it's transmitting, and the green light for receive will come on the other one with very, very low latency. So that's the general piece I've been working on for a while. What I've been doing this weekend is I've hooked in in the old radio terms we'd call this phone patch. So we can now dial in from the PSTN. So we'll use a carrier into Jambonz, which we just dial a number and basically we just get connected instantly. And now through DTMF, I can control, I can talk to these units. So first of all, we just join the channels. They're both on channel 1. I'll just send a 1, and let's put it on speaker so you can hear. And then what we're using is the star and hash, because obviously with a phone call and DTMF, you don't really have a push to talk. I can't hold down a DTMF key while I'm talking, so it's kind of a switch mode. So star is transmit, start, and hash is release, is end. So if I press star, we'll hear a little tone, and we should see the green lights come on both. There, and now, if I talk into the phone, oh, this one's got a slightly loose solder connection on that board. 1, 2.
1, 2.
But there's the audio coming through. So that's coming out the speaker, it's really the feedback. And if I press hash, it releases and we stop transmitting. Similarly, I can change channels. So if I tell this one I'm going to change to channel 2, and obviously I've got nothing to receive on channel 2, but if I transmit, we see, although we're transmitting, neither of them are actually receiving because they're only listening on that channel. Stop that one. If I change back to channel 1 and then transmit again, and we're connected. And we end. So let's hang that up. Yeah, basically that's what we've done. So we've got an existing project I'm working on, which is a push to talk in a microcontroller, in a $5 kind of or $10 very cheap board, very low power. These are currently connected over USB just for power, but the intention is to get this down to something about the same size as the actual Pi Pico itself, like a little shim board that sits on the back of it with a speaker, a microphone, and a small battery, and you have a tiny wearable push-to-talk device that can work between them, some control for channels and things. But we can now with Jambonz dial in via the phone network as well and bridge the two.
Cool, so let's talk a bit about how this works. What we have, hopefully you can see this mouse pointer, is we have our little microcontroller boards over here. So as I say, this important thing to note here, this is a microcontroller. So there's a Raspberry Pi, it's a Pi Pico. This is like an Arduino or an ESP32, one of these kind of super low power boards. This doesn't have an operating system, this isn't running Linux, this doesn't have a full-blown SIP stack and audio stack and all of that. This is just running in MicroPython. That's making an MQTT connection. So MQTT is a very lightweight kind of Internet of Things protocol. It's a publish subscribe to a broker, which is called Mosquito, just an open source application broker, over the Wi-Fi connection. And MQTT has a concept of channels anyway, or topics. So that's our fundamental basic connection from the broker. The code on here is doing audio, so speaker and microphone I2S control protocols, so digital audio protocols, into turning that into MQTT frames of 16-bit, 16 kilohertz LPCM audio. So we're sending streaming audio back and forth over the MQTT. Everything is then, the actual application logic is controlled by an application server. That's what I've mostly been writing. This is all written in Node-RED. I'll come back and show you the flow for that. That's all done in a low-code tool. Node-RED is very good for MQTT and that kind of thing. Now, the new bit that we've been building, or I've been building this weekend, is the integration with Jambonz. So Jambonz has the regular REST, call comes in, and what we do, we're using the listen verb, which creates a WebSocket connection from Jambonz to our application server, and the audio from the call starts coming in over the WebSocket. We can also pick up DTMF events on this WebSocket. So Jambonz is configured so when a DTMF tone is sent from the handset, it's an event that's sent over the WebSocket, and those are our control messages. So say the star and the hash to control the transmit and receive, and the numbers just to pick up channel changes. So the audio is constantly coming into the application server because it's a PSTN call, but then when we see a star message being sent, the application server knows the WebSocket connection and knows the channel it was on, and puts that into transmit mode and starts sending out over the MQTT those audio packets. So we bring in the WebSocket audio, we convert it into MQTT frames, fairly similar frame payload, and publish that down, and that starts coming out of the speaker on the devices or multiple devices. So all of the broadcast is done by MQTT. Equally, I didn't show it in the video, but it's a two-way channel. So if this one starts transmitting, again, you press the PTT button here, and it will start publishing audio over MQTT. That's picked up by the application server. We have to do a bit more work then to frame that into base64 encoded data and send that back over the WebSocket to Jambonz, and the call will hear that on the other end. So what we then have is a two-way speech, I suppose it would be known as half duplex. So one person talks at a time, and that's what the push-to-talk controls. So when you take control of it, you're transmitting, nobody else can transmit, and then you release and you're in listening. So when you're just dialed in and on the call, effectively the phone is in permanent receive mode, and as soon as somebody transmitted, the phone would play out the audio. So this is my code, so to speak. This is my application server. This is the flows I've been building in Node-RED. So quick walkthrough up the top. If you're not familiar, Node-RED's a low-code visual programming tool, so event-driven applications. So you can have these different sort of flows where everything's connected in. So this top one's a fairly simple. This is the webhook from Jambonz for the incoming call, and we just return a bit of JSON to Jambonz that says connect to the WebSocket. We're just handling the statuses there. There's some setup we're doing up here where those tones that you heard being played out in response to the star and hash, we're just kind of reading those into the local storage, so I don't have to read them from the file system every time I want to play them. So I'm just doing the base64 encoding and storing those two objects. Now this is our WebSocket flow, which is the main thing up here, WS socket. So you can see at the moment it's disconnected because there's no active calls. But whenever a connection or a message comes in over the WebSocket, we tag it with the appropriate channel that it's on, and if the phone's not connected to a channel, we just set that to null. We are then doing a switch here, so we're determining, is this an audio message, an audio frame coming off the channel, or is this a JSON message, so a control message like DTMF or some of the acknowledge messages. First of all, we'll look at the DTMF path, so we just JSON encode that. We check it is actually a DTMF because a few other events that are sent. And then we look to see what the tone is. So this is if it's a star, a hash, or anything else. If it's a star, we create the play audio frame, which is using that up tone that you heard on the thing. We set that. We put the system into transmit mode, and we send that back. So we do two things. The tone, it actually forks off here. We play that, send that tone back over the WebSocket, so you hear that tone being played out over the phone, but also putting the system into transmit mode, and we publish that out to MQTT. So this is the flow here, set flow TX. switches on a gate above it, and this says talking, which basically turns the red lights on the receiving units. And similarly, when we receive a hash, we do the same thing. We play a different tone, and we put the transmit mode into false and send that down. So that's our control path up here. Just down here, if it's digits, we just wait a couple of minutes, so you can support a kind of a 3-digit channel number if you want. So if you get 3 events in quick succession, so 1, 2, 3 as a channel number, it'll join those together into a single channel and set the channel that WebSocket is on. So this is our channel change control, really, just for keeping a record of which WebSocket or which call is on which channel. Then we have our audio path, which is actually much simpler. So the audio messages come in, again we tag them with the channel because we know from the WebSocket connection which channel the call is on, and this is a switch mode where we're checking if it's in transmit mode. So if it's in transmit, we allow it to pass. If the system's not in transmit, we don't, we just drop the messages there. We set up the topic, just doing a bit of encoding for the MQTT, and we just send those messages straight out over MQTT. So actually the audio path is fairly short. It's just this top, there's just a couple of gates and a couple of bits of labeling that are done on every frame. These are, so they say 16-bit, 16 kilohertz audio frames. So they come in, I think that's one every 20 milliseconds p time. So 50 messages a second flowing through here and out over MQTT. So that's, but you can hear the latency is very low. Similarly, just the stuff coming back, the two-way audio. So if messages are received on MQTT, what we're doing is we are just doing something to drop any WebSocket traffic, just to remove a loop, because if there's other things published, so the stuff's labeled if it's originated from a WebSocket, we don't want to create an audio loop. We do a bit of tagging and labeling. And moving around. Then this is our switch to determine if it's audio or signaling. We're ignoring signaling from MQTT in this, but if it's audio, we wrap this up. This gets the right channel number ID again for the WebSocket, mapping the channels on MQTT to the WebSocket connections. This time we have to actually base 64 encode the audio, because although Jambonz sends us binary frames, sending it back, the audio has to be base 64 encoded. So these are base 64 encoding the payload of audio, wrapping it up in some JSON and pushing that out on the WebSocket, which Jambonz then plays back over the channel. This is actually slightly longer audio frames. So whereas receiving is 20 milliseconds, we're sending back 200 milliseconds. So same rate, same sample rate, but the frame size is a little bit larger, just to remove some of the overhead. So it's it's maybe 200 millisecond latency on the transmit that side, but it's pretty much indistinguishable. Certainly for push to talk, this is pretty good. As I mentioned just on the demo there, those dev boards that I was showing are the kind of the large big ones. These are the iterations I've been working on to get down to something smaller. So you can just about see this little one here with the buttons, and you can't really tell, but there's the audio components are on the back. That's it with a Pi Pico W. That's the size of the battery that I'm looking. So that battery will sit in between the two boards. The whole unit will be a bit bigger than a packet of chewing gum, really, into a little 3D printed case. And these are a couple of other iterations on the boards. So I'm still trying to debug some of the hardware. My soldering skills for very small surface mount components aren't quite good enough.
So one thing I didn't perhaps show completely was that also we have two-way audio. So not only can we transmit from the phone to the device, but equally from the device we can talk into the radio and it'll come out the phone. So if I put that one there, which was on speaker, and I transmit on this one, you should hear some audio. 1 2 1 2 1 2. It's a little bit quiet. Let's just turn the volume up. 1 2 1 2 1 1 1 1 1. Testing 1 2 3. So it's a little bit choppy. That's a timing issue with these round microphones, especially. But yeah, so we have two-way audio, and again, just to show you, transmit on the phone, and the audio on the phone is coming out of a very small speaker here, and end.
Cool. Well, that's it. Thank you very much. That's my website there. You can find all the details about me. There's not a lot of stuff on this project online yet. I'm still kind of figuring out some of the bits of the, especially the code on the microcontrollers. But at some point, hopefully in the next, well, probably 6 or 12 months, I'll be able to publish a full demo and the finished boards. Thank you very much.